Good morning everyone. My name is Pranay. I am from CSC AML section C. Today my topic from the subject engineering physics is amorphous solids. I would like to introduce and I would like to give a small introduction about the topic amorphous solids. The amorphous solids, they represent a distinct category. They represent a distinct category of condensed matter that occupies an intermediate state between the perfectly ordered crystalline solids and highly disordered gaseous states. The term amorphous itself is derived from the Greek word amorphous, with meaning without form, referring to the absence of well-defined long-range repeating arrangement of atoms or molecules. Unlike crystalline solids, which possess highly regular geometric configuration, amorphous material lacks such periodicity, resulting in unique mechanical, optical, electrical, and thermal properties. These features make amorphous solids indispensable across scientific, engineering, and industrial domains. Amorphous solids are sometimes referred to as non-crystalline solids, pseudo-solids, glassy solids, or supercooled liquids. Although they behave mechanically like solids, their atomic arrangement resembles that of a liquid frozen in time. Their physical behavior, structure, formation methods, and applications reveal the remarkable versatility and significance of these materials in everyday life. Next, I would like to go to the point characteristics of amorphous solids. Amorphous solids possess several distinguishing characters that set them apart from other states of matter. One is lack of long range order. Crystalline solids expect repeating structural patterns in 3D method, whereas in contrast the amorphous solids, they show only short range order, that is the atoms are ordered only to over short distances, a few typical atomic diameters. Beyond this, the arrangement becomes random, so the atoms or the amorphous solid pattern, it is arranged in a random way. And next is isotropy. The amorphous materials are generally isotropic, which means their physical properties remains the same in all directions. The uniformity arises from the absence of regular atomic arrangement. For example, optical glass displays the identical refractive properties regardless of direction. Gradual softening. Unlike crystalline solids, they have sharp melting point, whereas amorphous materials, they get softened when they are heated because they have very low melting point and very moderate melting point, that they can be easily heated. So due to this variation, we can see that with the behavior of amorphous solids is associated with glass transition temperature Tg, supercooled liquid nature. Amorphous solids are called as supercooled liquids, as previously we explored. Why? Because they do not achieve or attain thermal equilibrium and are frozen in disordered states. Whereas mechanical behavior, amorphous solids may exhibit brittle or ductile behavior depending on the composition and temperature. Glass, for example. Whereas thermodynamic properties, these materials do not profoundly or possess the perfect heat of fusion. Thermodynamic state is different from that we see from crystalline state. So these are the basic things or characteristics of amorphous solids that characterize them into the characteristic of amorphous solid. Whereas let us know the differences between the crystalline and amorphous solids. So let's see atomic arrangement. They are long range order. These are no long range order but short range order. The melting point is soft and fixed, and the melting point is gradually softening. Isotropic. Crystalline solids are usually anisotropic, whereas amorphous solids are isotropic. Mechanical strength high and direction dependent, generally lower and direction independent. Heat of fusion well defined, and heat of fusion is not well defined for amorphous solids. Example, NaCl, quartz metals are examples of crystalline solids, whereas glass plastic gels are example of amorphous solids. Structure of amorphous solids. The atomic or molecular arrangement within amorphous solids resembles that of liquids. Key structure aspects include like short range order SRO. Atoms remain bonded to few nearest neighbors in a predictable geometry, typically snapping limited distance. This short-range order is responsible for basic stability and bonding. Absence of long-range order, as we know that these are short-range order and long-range periodic arrangement is absent in amorphous solids. So, due to this lack of symmetry accounts for optical and mechanical properties like isotropy, atomic packing density, amorphous solids tend to have lowering packing efficiency compared to crystalline solids. The random arrangement leaves voids at micro and nano scales. Random network structure in glassy materials such as silica, glass, atoms form a random network rather than organized lattice. Topological disorder, the angles and distances between atoms fluctuate rather than being constant or being fixed. Formation of amorphous solids. Let us learn about formation of amorphous solids, the steps, the mechanisms which we use. First of all, rapid cooling. So the molten materials, these are cooled by the process crystallization and they form glass, common in silica glass manufacturing. Mechanical grinding. So the prolonged milling can break long order producing amorphous powder. Vapor phase deposition. Thin amorphous films can form vaporized materials deposited on cool surfaces. Sol gel process used to create amorphous silica and ceramic coatings. Irradiation and pressure techniques. High energy radiation or pressure can disrupt crystalline order. And polymer solidification. Many polymers naturally form amorphous state due to chain entanglement. Types of amorphous solids. Amorphous solids may be classified into several categories. Let's know first category, glasses include silica glasses, borosilicate glass, soda lime, and germinate glasses. These are rigid, brittle, and widely used in optical and structural applications. Polymers. Certain polymeric materials such as polystyrene and polycarbonate exist predominantly in amorphous states. Metallic glasses formed by rapid cooling of molten metals. They have exceptional strength, elasticity, and corrosion resistance. Amorphous semiconductors. Amorphous semiconductors such as silicon are used in solar cells and TFT screens. Organic amorphous solids. Organic amorphous solids, pharmaceuticals, and certain organic compounds for amorphous states to enhance solubility. Gels and colloids, these can be considered amorphous due to random arrangement at microscopic levels. Properties of amorphous solids. Amorphous solids exhibit unique physical, mechanical, thermal, and chemical properties. Physical properties. Transparency is one of the physical property. The next physical property is isotropic behavior. Third physical property is variable density due to irregular atomic packing. Fourth is lower hardness compared to crystalline analogs. Mechanical properties. Brittle failure in glass material. High elasticity in metallic glasses. Resistant to crack propagation due to lack of slip planes. Thermal properties. Glass transition temperature instead of melting point. Lower thermal conductivity. Wide softening temperature range. Chemical properties. High corrosion resistance except especially in metallic glasses. Lower chemical reactivity in silicate glasses. The optical properties are excellent light transmission used in lenses, fibers, and displays. Mm, Glass transition temperature, it is an important concept in amorphous solids. Definition is the glass transition temperature is the temperature at which the amorphous solid transitions from hard brittle state to soft rubbery state. So hard brittle to the soft rubbery state is only called as glass transition state temperature. Significance is critical in polymer processing, affects mechanical strength, important for pharmaceutical stability. Factors affecting glass transition temperature is molecular weight, degree of cross-linking, cooling rate, plasticizers, and applications of amorphous solids. Amorphous solids find extensive use across science, technology, and industry. Glass industry, windows, optical lenses, laboratory glassware, smartphone screens, electronics. Amorphous silicon is used in solar cells and LCD TFT techniques. Dielectric layers, magnetic storage materials. These are the various applications in as amorphous solids we use. Pharmaceuticals, the amorphous drugs often dissolve faster due to high surface free energy. Construction, glass fibers, insulation materials, and architectural components. Automotive and aerospace, metallic glasses for gears, springs, and coatings. Yeah. Metallic glasses, a modern class of amorphous solids. Metallic glasses form through extremely rapid cooling of molten materials. Properties: very high strength, high elasticity, low magnetic losses, corrosion resistance. And the applications of metallic glasses is sports equipment, transformer cores, surgical tools, precision instruments. Thermal behavior of amorphous solids. These solids lack a clear melting point. Softening rains, they soften over broad temperature before becoming liquid. Heat capacity, they show changes in heat capacity around Tg. Conductivity, they have generally low thermal conductivity due to random structure. Future prospects of amorphous materials. In the future process, they are expected to play a big role or a major role and a very good role in future applications. It may be in flexible electronics, high strength alloys, biomedical implants, advanced optical sensors, energy efficient transformers, research strength, tailoring amorphous structure for specific properties, developing bulk metallic glasses, nanostructured amorphous coatings. Conclusion: amorphous solids form a fascinating class of materials that bridge the characteristics of liquid and crystal. With this, I conclude my topic of amorphous crystals, and I hope everyone are clear about my topic. And thank you everyone for giving me this topic. And I'm very happy to explain this topic. And I'm concluding here. Thank you everyone. Thank you.